Okay, welcome to example 2 on page 115 of the workbook. And this is another example of taking a function and building a Taylor series. We'll work through this together. This time they'd like us to build the Taylor series for the function f of x equals ln of x centered at the number a equals 1. So this is going to be the same process that we did in the previous example. Building a Taylor series is about taking derivatives essentially. So we'll start with our function ln of x. And what is the derivative of ln of x? Well, the derivative of ln of x is 1 over x, which we could also write as just x to the negative 1. Okay, second derivative. Derivative of x to the negative 1 using the power rule is just negative x to the negative 2. And we just continue. 2x to the negative 3. Let's do one more derivative. Negative 6x to the negative 4. Okay, and once we have those derivatives, we want to take the value of a that we're given and just substitute that into our derivatives one by one. So we're going to take 1 and just substitute it in for all of those functions that we have. All right, so if we start with f of 1 up here, we're plugging 1 into the natural log function, which is actually going to give us a 0. F prime of 1 is 1 to the negative 1. That's still 1. And then we're going to get negative 1 to the negative 2. The thing is that 1 raised to any power is always 1. Okay, so these numbers that we're calculating are going to be a little bit predictable. So 2 times 1 to the negative 3, that's going to be 2, and then finally negative 6. You can double check those calculations. Okay, so what does the Taylor series look like? Okay, well, we have a formula for it. Let's start by writing that down. Okay, and I'm going back to page 113 and just writing down the definition of the Taylor series here with a equals 1. So we're going to get f of a, which is f of 1, plus f prime of a, f prime of 1 over 1 factorial x minus 1, okay, and again, this is just the formula back from page 113, where we wrote down a general formula for the Taylor series. And what do we actually have to do to get a final answer here? Well, again, it really just comes down to filling in these derivatives that we calculated above. Okay, that's all we really need to do here. So for example, f of 1 is 0. We can see that up here. F prime of 1 is 1, so we'll fill that in. Okay, f double prime of 1 is negative 1. Then we come to 2 over 3 factorial. Negative 6 over 4 factorial. And so on. Okay, so what we just wrote down in the last line, that would actually be an acceptable final answer, what we have here. But in this case, it's instructive to maybe go one more step. There's sort of a pattern to these numbers that we're seeing here. Okay, so first thing, we notice we've got a 0 for the first term. We don't really need to write that. And then what's 1 over 1 factorial? That's just 1. Okay, and then we come to minus 1 over 2 factorial. That's a minus 1/2. And then 2 over 3 factorial, what is that? Well, that's 2 over 6, which reduces to 1/3. Okay, and then we come to 6 over 4 factorial. That's 6 over 24, which actually reduces to 1/4. Do you see a pattern here with these terms? notice that the denominators are getting bigger by 1 every time, and the signs are alternating. That's the other thing that's going on. Can you predict the next term here? Okay, I would predict a plus 1 over 5, x minus 1 to the 5th, and the pattern would just continue. Okay, and so there's our answer to part A. That is the Taylor series for the function natural log of x. Okay, and just as in the previous example, part B asks us to take this series that we just found and to do some approximating with it. Okay, so we'd like to use the first 3 Taylor polynomials to approximate the value of ln of 1.05. So how about if we start by using our calculator just to calculate ln of 1.5 so we kind of have a basis of comparison here. Okay, so you can double check this, substitute this into your calculator, and what you should get is 0.048790, and this just continues on. Okay, I'm just writing out the first 6 decimals or so. Okay, we'd like to do approximations with these 3 Taylor polynomials and just see how those numbers compare to our calculator's value up there. All right, so let's do that below. Starting with P1 of 1.05. Okay, and remember again what P1 is. Okay, that's asking us to go back up to our Taylor series up here at the top of our page and just take enough terms in the series until you reach the first power of your variable, which would actually be sitting here, x minus 1 to the first. So we want to just take that first term, x minus 1, and substitute 1.05 in for x. Okay, what do we get if we do that? Just leave a little space maybe and put that way over here on the right. 1.05 minus 1 is just 0.05. That's our first approximation. Notice that it's already at least reasonably close to our calculator's answer. Okay, let's do P2 now. We'll hope that that approximation is even closer. Okay, so P2 is just the polynomial that we would get if we go out in our series until we reach the second power. Okay, so we're going to stop when we reach x minus 1 squared. So we're going to take just those 2 terms that I underlined and plug 1.05 in. Okay, and you can do that calculation on your calculator and just confirm that if you do, you get 0.04875. Okay, notice that that number is even closer to our calculator's number, and that's what we would predict since Taylor polynomials, we observed that they can converge to the function that we started with. Okay, and then finally P3. Same deal. This time we're going to go out in our series until we get to the third power. So we're going to take those first 3 terms that I underlined, substitute in 1.05 for all of the x's, and here's what we're going to get. Okay, and you can confirm this calculation as well. This time we're going to get 0.0487917. And notice that that third number, that is even closer to the number that our calculator gave us at the beginning. And that's the idea of this. We'd like these Taylor polynomials to converge to our function, and we can see that we're getting that behavior. Each approximation is a little bit closer than the one before it.